Okay. Shall I start? Yeah. Okay. So good morning. This is the last lecture, and let me start by summarizing what we did last time. So basically, last time we proved the following thing. We showed that in the particular limit we are interested in, which is first thermodynamic limit, then this particular scaling limit, we can replace the state in the expectation value of any local observable with a stationary state. Okay? And this stationary state depends on this I called it zeta, which is the ratio of position of observable and time, which is kept fixed in the limit. Okay? And what we were saying at the end of last lecture is that we had a hard time to compute this thing, but actually it can be computed much more easily. And that's what we are going to do today. So, again, yeah, let's. I don't know actually. I don't remember this used by Jerome. But it's very simple. You just take the scaling limit x and t to infinity with a fixed ratio. This ratio is called ray. That's it. So I'm saying that all the calculation we did last time can be avoided if we assume something like this. All right, but we don't know what is the state, what is the stationary state. So we assume that, and now I will give you a procedure to compute, to determine this stationary state without doing the calculation we did last time. All right? And then we will see that this procedure can be applied also in the interacting integrable case. And that's the whole point. So we can basically determine such a stationary state, if it exists, in a very simple way. Okay? Is it clear at this point? Good. Okay, so now we are going to assume this. And we are going to determine rho s. Okay. In order to determine this state, we are trying to get some intuition from the literature on homogeneous quantum quenches. So for homogeneous quantum quenches, what one normally does is something similar. But in that case, the stationary state doesn't depend on the ray, it's constant. And that's clear because if the homogeneous by homogeneous quantum quenches, I mean a quantum quench where this state here doesn't depend on position at all. So basically, you can always shift away this x dependence. Okay. So in that case, you basically have that the limit of infinite times. In the limit of infinite times, you can replace this state here with the stationary state. And to determine that stationary state, what you normally do is you try to fix it by looking at the expectation value of local charge densities. Okay? So let's try to see how it works in a simple case. So let's start from a warm-up. Okay? Assume assume that the state rho of t is invariant under translations. So this is not our case, it's just a simple example. Okay? But it's not stationary. So in that case, basically our identity we have here, I mean our requirement, becomes just the limit of the thermodynamic limit and then the limit of infinite times, as we said. Okay? And also, let's remember that we have a set of conserved charges that commute with the Hamiltonian, which means, as we said in the first lecture, that the densities obey a continuity equation. Okay? All right. But if you assume the state here to be invariant under translation, and we take this expectation value, what do we get? Is a question to the audience. What do we get from that expectation value? Sorry? Somebody answered? No.
Yes, you sum over J.
No, I don't sum over J. So I really take that expectation value. But on the right-hand side is the same operator, just shifted, okay? Since the state is invariant under shifts. Yeah. Okay, so basically we get this.
There's no symmetry then.
Exactly. This is a simple example where we assume transitional invariance, which is not the case we were doing before. So here. Okay. Which now, using our assumption, means that the expectation value of the charge on our initial state must be the same as that on the stationary state. Well, so here, let me just finish writing. So here I'm switching between Heisenberg and Schrödinger picture. Okay, but it's equivalent. Okay, so we have something like this. But now we just remember what these expectation values look like. Okay, so we know these things, we computed them. So if we represent our stationary state using the root density, what we have is that this side here in the thermodynamic limit becomes that's at least, I think, the notation we were using before. Yes. So note that this one is the root density representing this state in the thermodynamic limit. Okay? While on this side, we have something like integral in dk rho 0 of k qn, where I defined rho 0 as where I define rho 0 as the expectation value of the mode operator on the initial state. Okay? Question. Is this rho 0 fully determining the initial state can be considered a root density? The answer is no, because the state here is not stationary, so it has much more information. It contains more information than that. It's not just okay. So I'm saying that. So this is just an identity from here to here. I just plugged in the form of the charges I gave you the other day. Okay, and I took the thermodynamic limit, and I found this expression. Okay, and this expression depends on this rho 0 of k, which is defined as follows, right? But I'm saying that so in the previous lecture we introduced this concept of root densities, and we said that stationary states, or more precisely eigenstates of the Hamiltonian, can be represented in the thermodynamic limit by that function, by root densities. I'm saying that since this is not an eigenstate of the Hamiltonian, it's not totally represented by this. Not all the expectation values on this state here are written in terms of this function.
Okay, so it's a random initial state.
Exactly. Good, but then we have that identity, which can be written as dk qn of k, and then we have rho s minus rho 0 of k equals 0. Okay, and this is true for all the charges, and we said that this one is a complete set. This qn is a complete set, which means that this equality here becomes an equality of the integrands. Okay, so this means that rho s is equal to rho 0. Yes. Yes. So basically, as we will see shortly, this procedure can be repeated in the interacting case. But this step here is highly non-trivial. So to extract this function here in the interacting case is hard, and this can be done by, for example, the quench action method. Okay? This is a very complicated step in general. The problem is that it's not obvious to how to express this function in terms of the initial state, right? Yeah, because there is no. I mean, the main difference between an interacting integrable and a free model is that there is no well-defined concept of mode occupation numbers operator. Okay, so you will have something similar to you have root densities, as we will see, but you will not have that operators. And that's the problem. Okay, but we found this, okay? So we found the root density of the stationary state. All right? So we fixed it. Okay, this is fixing the stationary state. Good? Okay, now let's try to repeat the same procedure in our case, because remember, this was a simple example where we assumed the initial state to be transitionary invariant. Okay? Now let's start doing our case instead. So we erase this. Okay? We erase that. And now, do you see problems like, what can we do? So first of all, now we can't say anymore. We can't say anymore that this here is true, right? This equation won't be true anymore, obviously, right? Because now when I take the expectation value of that, I get something non-trivial on the other side. Okay, so something one can say is, let me sum over all the sides, okay? I sum over all the sides, and then I divide by L. And then I take the limit. Is this going to give us enough information? Is it going to fix the state or not, in your opinion? No, and the reason is quite simple, is because if we check our result we obtained last time, we see that there is this, a structure like this, right? So there is a stationary value on the right, the stationary value on the left, and there is some non-trivial stuff here, and the region where the non-trivial stuff happens is of size t, okay, in the thermodynamic limit. So this is of size t, while this here and this here are infinite. So if I consider the average, if I consider something like sum over j of the charge density at site j, this one will contain 0 information about this. Okay? It will just be killed, because L is much larger than t, and in the limit we are considering is actually infinite, while t is finite, because we take the thermodynamic limit first.
Will be washed out then.
Yeah, it will be completely washed out. So this is not good enough. So, okay, but then let's indeed take the expectation value of what we have. So, in other words, we take that equation, we take the expectation value, and what we find is, of course, that we need to add stuff. Jt rho of 0 minus trace j minus 1t rho of 0 is equal to 0. Okay? So now this is actually true. All right? And now let's try to take the scaling limit of this equation. Okay? So we take the limit t. So everything now, I assume, is already in the thermodynamic limit. So I will not write thermodynamic limit anymore, just to make expressions a little bit more compact. And let's take the scaling limit. Of course. On the first term is still rho 0, correct. And this is a hot. Okay, good. So let's take the scaling limit. Let me note that to take the scaling limit and get a finite result here, I should multiply by j. Or by t. Let's do it by t. Then let's plug this thing. And what we get is the following expression. Okay? So we get that the derivative with respect to the ray of this thing, which is the expectation value of the charge density in the stationary state defined by C. But I mean, we have this relation. Okay? Okay. And now we are just going to use this relation here to fix the state, very similar to what we did before. Before that, let me note the following thing. Let me note the following thing. So this we did here was for a fixed ratio. But if we assume that there is a finite speed for the propagation of information, then there will be a value of this ray such that if I move at large enough speed, I'm just seeing only the state on the left or only the state on the right. Okay, so you remember I had this light cone region I just erased. I'm just saying that if I take this ratio large enough, I will always be here. Okay? And if I take this ratio large enough in absolute value but negative, I will always be here. Okay? This means that I can immediately find some boundary conditions, if you want, for this equation. The boundary conditions are just that trace rho s plus or minus infinity q and is just equal to the value of the density on the left or on the right. Okay? So this is just right, left, q, 0, n. Okay? Those are the two states I joined at the beginning. Those the thermal states at temperature T right and T left. Is this point clear?
Yeah, I don't understand the above equation. Could you say how we produce the right-hand side?
Yeah, sure. Let me just try to separate the two. Yeah. So it's very simple. You just okay. Let's start from this bit. Okay. So. So we are trying to show this. So we start from this expression. We use our assumption, which is that in the scaling limit you can replace this state here. So let me put the time dependence on the state. It's more convenient. So in the scaling limit, you can replace this state here with a stationary state. Okay? And let me also rewrite this derivative in terms of a derivative with respect to the ray. So and I had t, right? So ray is equal to x over t. So derivative with respect to time is equal to the derivative with respect to the ray. Times the ray. If I fix x, do you agree? Yes? So this is equal to minus zeta, the derivative with respect to zeta of z j, and then you take the limit, and you replace this state with a stationary state. So you take the limit. This gives you that'd be right. Yeah.
And then the last one, why did you merge the other two together?
Because I'm basically expanding this. So you see that this term here is computed in j, and this term here is computed in j minus 1. And I know that these two things become functions of the ray. And the ray corresponding to j and t, so j over t, is very close to the ray corresponding to j minus 1 and t. Actually, it's the same. So at the first order, these two terms cancel, and I need to expand this term, and this is what is giving me this derivative with respect to the ray.
Okay, why j not there? Because like...
And everything here, since this state is by assumption translational invariant and stationary, everything can be computed in 0 or in another point, your favorite, because the state here, it's invariant under translation. So I can just move the point where I compute the observable. Right? So here I put 0 just for like to put something. I mean, we can put 1, 2, whatever. Every side, yeah. No problem. Okay. Yeah, so it's, is it clear? Any other question on this? Yeah. Okay, so that's a good point. So I assume there is a maximal velocity, but I don't know the value of this. I don't know the value of the maximum velocity. No, because, I mean, I have a bound. So, for example, in a relativistic theory, well, yes. But in a spin chain, what you have is the so-called Lieb-Robinson bound. Yeah, but you don't know what it is, and and it's not always reached. So it's just a bound. It just tells you that there is a maximal velocity, but depending, as we will see, depending on your state, actually, you will have different maximal velocities.
So for free fermions, there's no...
For free fermions, yes, the maximal velocity is just the maximum of the dispersion relation, as we will see in a second. But for XXE, it changes. It depends on the state, as we will see. Other questions? No other questions. So, okay, good. Then we just use this equation to fix the state, as we did in the simple example before. So, what we need to do is very simple. We just plug in the expression of the charges and the currents we have. Okay? We have the expression for the expectation values of charges and currents. I gave you this expression in the last lecture. Okay? So we just plug in. We know that the expectation value of a charge is integral decay Qn. Okay, so this is the expectation value on the state described by rho. Okay? And the expectation value of a current in the same state is Qn. Okay? This is n, this n, is Vk rho k. Okay? Okay, so if I now express this, what I find is the following. I find that this equation, minus 3 is equal to this. And this is equal to 0. Okay? Where this is the root density of rho s of zeta. So clearly it depends on zeta, on the rate. Well, but that's it. Because now we just use the completeness of the set of charges as we did before. Okay. So complete. So this means that the integrand again should vanish, and we find this equation. Okay? Any question on this step? No. Good. So, we found this equation, which is a main equation of the lecture. And note that from these boundary conditions here, from these conditions here, if I just do the same, I replace the expression of the charges and so on, this just gives me that rho of infinity is 1 over 2 pi trace and rho minus infinity is 1 over 2 pi trace rho left and of k. Okay?
So the velocity cannot be taken out of the derivative?
It can.
Okay.
But, well, we will discuss that. Yeah, please. So V, in the previous lecture, we just saw that for the free fermionic case, V is just the first derivative of the dispersion relation. In general, we will see. That's the point of this lecture. But for free fermions, it's just the first derivative of the dispersion relation. Okay? Good. So we found this equation, and how can we solve this equation? It's very simple, right? I mean, you just, as we noted, you can bring this V out. So this equation is just telling you that the derivative of rho with respect to zeta times this function, V minus zeta, is 0. Which means that either this or this is 0. So the solution to this equation is basically just a step function. Okay? Sorry? Yes, for I fixed k fixed. And for each k, this is just a step function. So this will be rho of zeta and k equal to some rho left plus rho right okay? And now, how do I fix these two? I just use these boundary conditions. Okay? I just use the boundary conditions. So, let me call this one rho left and this one rho right. Sorry, obviously the other way around. Exactly. Exactly. So the interpretation of this equation here is extremely simple, right? It's as follows. So basically it's like this equation can be interpreted really as a, let's say, kinetic theory for classical particles that are moving freely. So the idea is that at the beginning you have two reservoirs, one on the right, the one on the left. You produce in the right reservoir the distribution rho right of k, which is a momentum distribution of some classical particles. You do something similar on the left. Okay? You let the system evolve, and then you look at what happens at some ray. And then what you see is that you see the left distribution for all the particles that are faster than you. So you are moving away from the junction along this ray, and you are reached by all the left particles which are moving faster than you. Okay? So all the particles that are faster than you reach you. While instead, you are reached by the right moving particles if they are slower than you. For example, like this. Okay? This is the simple meaning of that solution. But note that this is exactly the result we found from the exact calculation. So this is the result we had a lot of troubles in determining in the previous lecture. Right? And so here we found it in a very simple way. Good.
let's get to that point. Yeah, this is a good point. So let me first summarize what we did, and then we move to the more interesting case, which is the interacting one. So basically, the key of all our derivation is at the end of the day this equation. And we determine this equation by looking at the continuity equations of all the conserved charges of our system. So this kind of treatment is now known as generalized hydrodynamics, GEHD. And what we just did can be repeated with like basically no modifications for all free systems. And by free systems, I mean systems where I can map the Hamiltonian in something of this form. So independent, a sum of independent mode operators, okay? And these operators can be fermionic, which means that the square of themselves is equal to themselves. So fermionic. Or can be bosonic. So n, k, 0, 1 to infinity. Okay? So in this case, actually we have the exact expectation value of the currents. In this case, well, nobody computed it exactly in this way, but well, you can find directly this equation in free modeling with a different approach. But so it holds, even if nobody computed exactly J. Okay, but the real question is, what about integrable models? Can we, interacting integrable models, can we generalize this treatment to the interacting case? Okay, of course now the answer is yes, but to explain you how to do that, I need to introduce a little bit more of formalism. So I have, let's say, 20 minutes before the break, and it's hard to explain Bethe ansatz in 20 minutes. So I will not try that. But I will try to give you, let's say, the main ideas, comparing with what happens for free systems. Okay? Good. So the main idea of Bethe ansatz is that you can still construct the eigenstates of your Hamiltonian in a, like, with a similar idea to the one you use for free systems. So for free systems, we saw that we can construct our eigenstates as scattering states, so a collection of particles which are non-interacting and have momenta k1, kn. Okay? For in the Bethe ansatz eigenstate has a similar form. So it's again some combination of, let me call it lambda, of particles, can be taught as a combination of particles with different momenta. Okay? Now, to cut the long story short, what you find is that in the interacting case, you need to introduce many different species of particles. Okay? So here we can at least do everything just with a single species of particle. Here instead we will need to introduce many different species of particles. Okay? And at the end, we saw that in the thermodynamic limit here, so TL, you can describe your state using just the root density. So basically the density of the particles in your state, the momentum distribution, you can view it, of the particles describing your state. In the interacting case, you will do something similar. And you will have something like that. You will have a bunch of different root densities, one for each species of particles. One you have in your state. Okay? Good. Good. Another important difference you will find is that in this case, as we saw, you have some simple quantization conditions for the momenta. So you have that all the momenta are basically Kn, Kj is just 2 pi over L times the number Nj. While here, the quantization conditions will be much more complicated. The quantization condition for the value that the momentum Kj will assume, or lambda j will assume, will depend on the value of all the others. So, in other words, the quantization conditions will depend on the state. Okay, so this is probably, it's not very informative, but the main point is that here you have that density of, you remember, another way of picturing this state was, you can draw a line with holes. That represent all the possible values you can have of your momenta, and then you fill some of them, right? You fill this one, this one, this one, this one, and this represents your state, okay? But the density of these holes here is very simple to compute. It's just found from the quantization conditions. So it's just 1 over 2 pi density. In this case, instead, will be more complicated, and it will be a non-trivial density, 1 for each species. So there will be another function called rho total, and okay, so I call these holes where I can, these slots where I can put my particle, I call it vacancies. So in the free case, the density of vacancies is just fixed, is 1 over 2 pi. In this case, it will be a non-trivial function, which I call rho total. Okay, so fine. But that's about it. That's about everything we need. Because again, also in the interacting case, these densities here will fully specify the eigenstates of the Hamiltonian in the thermodynamic limit, in the sense that the expectation value of every local observable will be, in principle, expressed in terms of these rows. Okay? Good. So what we need to do is just to find the expression for the expectation values of charges and currents. That's all we need in our procedure at the end, if you think about it. Okay? So the expectation value of charges, they look exactly, basically the same as the ones we already had. Now I'll define these things in a second. Okay, you see, this is basically the easiest, the simplest generalization of the expectation value of the charges we had before. It looks like before. I just added one other index, this m, that specifies the different species. Okay? In the free case, you had integral over momentum of q and times rho. Here, instead, I have a sum of different q's corresponding to the different species times different rows corresponding to different species. Okay? But apart from that, it looks exactly the same as before. Okay? So the question, and this one is very easy in beta ansatz to find. It's basically it's free. You find it immediately once you define your beta ansatz. You can find immediately this expectation value. The problem comes when you want to find the expectation value of the current. Okay? The expectation value of the current instead is in general very hard to compute. Also because the current operator is in general very hard to compute from the continuity equation. It's not a trivial task. Then you have to compute it and take the expectation value of that operator. And in general, for interacting theories, this is hard. But recently, an expression has been found, which is basically the same as the one I was describing you before for the free case. Okay? So you basically have the same form as the one of the charge, and you have to introduce an appropriate function that you call velocity. But this function here, as we will now show, maybe after the break, is what it contains all the information, all the non-triviality of this thing. Okay? And an important thing to note is that this expression here, as I said, is exact and very easy to verify. This instead is very hard and has been computed exactly only in some beta ansatz solvable model, thermodynamic beta ansatz solvable models. In particular, in the case of integrable quantum field theory that are relativistically invariant and have diagonal scattering. So in that case, you can actually compute it under some assumptions, but I mean, it's basically an exact result. But for example, for spin chains, there is no exact derivation of this formula. There is no derivation. For spin chains, this is just an assumption. Or better, I mean, you assume that and then you verify it in different ways. For example, this one can be verified numerically to high precision because this is a statement that you are making on a stationary state. So you can verify it numerically with DMRG, not TDMRG. It's an equilibrium property. Another thing you can try to verify is that like for some models, for example, the most famous interacting interval quantum spin chain is the XXE model. You have some identities among currents, and you can verify that this expression here reproduces that identities non-trivially. For example, you have that the energy current in the case of the XXE is conserved, is a conserved charge. And it corresponds to the second conserved charge. So you have that J1, or in my notation 1, is equal to Q2 in XXZ. This is highly non-trivial, of course. I mean, you should show that if you put the proper function here is equal to this expression with a different function, I mean, it's non-trivial, and you can verify that. Yes?
On the physical meaning of the matrix Q and M, so what do the indices N and M then mean?
That's a good point. So I recommend not to view it as a matrix. Why? Because the index N refers to the charge, while M, it's like if I change charge, I change the function. So it's basically that you give me a charge density. Okay? Previously that was specified by one function, Q n of k. But now instead is specified by a vector of functions. And you need one function for each species of particles that is characterizing your state. Okay? So that's it. So this index here is the one referring to the species of particles. And this one is for the charge. It's just telling you that if you change charge, you should change this function.
What do you mean by change charge?
Like, for example, if you look at the function characterizing the energy, is different from the function characterizing, I don't know, another conservation law.
Okay, the conserved quantity is okay.
Yeah. Yeah, sorry, yeah, I use charge and conserved quantity in the same, sorry, I'm sorry, this is, yeah.
So N is the number of conserved quantities.
It's the number specifying the conserved quantity. Yeah, so N. Any other questions on this? This is yeah, please. Well, I mean that's a good point. So as we know, in integrable models there are also odd charges that are odd under parity. These odd charges, I mean, for these odd charges you can define the current to be even. Okay. So, for example, you can compute this, the expectation value of such current on a thermal state, right? And it will not vanish. So it will give you a non-trivial check. So you will then compute according to this function the expectation value on a thermal state, and you will compare with the MRG. No, you find the expression. No, you find the, I mean, you can find the expression by hand of the first few. The problem is that this is a statement for all of them. So you will find the expression for the, I mean, if you just plug into the continuity equation, you can find the expression of the current. The problem is that you don't have a general procedure to find all of them at once. To find. No, I mean, no, you don't take the expectation value of the continuity equation. You use the continuity equation to determine an expression of J, and then you take the expectation value of J, and that doesn't vanish in general. Yeah, it gives you you have to fix a constant. Yeah, it's basically, yes, you have the derivative, you fix the current up to a constant, which is state independent, and then you basically evaluate it on a thermal state as a function of the temperature. This fixes the constant, and you compare with this. Yeah, no problem. So this is giving you a non-trivial verification of this identity. Any other question? No? Okay, so I think we can have the break now, and after the break we compute the velocity. Okay, So, any other question about what I was saying before the break? Everything is crystal clear? Good. Better. So, as promised, let's try to have a basic idea of what is VM you should put here. Okay? So, first of all, what was the velocity we were putting there for the free case?
The derivative of
Yeah, but why? Why the derivative of dispersion relation? It was the group velocity of elementary excitations, right? Well, so a good guess for what that V is could be exactly the same, right? Why not? Could be the group velocity of elementary excitations. Why? Good. So let's see what this thing is and why this is a bit more complicated than in the free case. So what is an elementary excitation? So let's picture my state as just a line with some empty slots and some of them occupied. Okay? This is my state. How do I make an excitation on this state? What do? I can't hear. I just put an additional ball or remove one, right? Yeah. But so, in the free case, this doesn't affect all the other balls. I just put one, and all the others stay in the same position as they were before. That's what leads us to find is a derivative of the dispersion relation. The main point is that in the interacting case, as I was trying to explain before, but of course it's hard if you have no idea what this beta ansatz is, whenever you add an additional ball to your state, so I add this, for example, right? All the others move. They move a little bit. They move like this, like this, like this, like this. Yeah, because exactly, this is precisely telling you that there is some interaction going on. So you add an additional particle to the state, and all the other get squeezed, they get moved. Okay. So if I try to find the energy of this excitation, what should I do? Of course, I should do the same thing I was doing before. I compute the energy of this configuration. Okay? And I subtract the energy of the initial one without the added ball. So 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so it's this, 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 and this, right? So I just subtract the energy of this configuration. But as we said, in the previous case, this one was the rapidity, adds rapidity lambda, at the momentum given by lambda. So this was just a function of lambda in the non-interacting case, right? But in this case, instead, it will be a function of all the others also. Okay? The same thing will happen when I try to compute the momentum of this excitation. Okay, so the energy will be some energy of, I add a particle with rapidity lambda and species n. So this will be En lambda, but it will depend on the full set of these rapidities. The same will be true for the momentum. Delta P will be some Pn lambda, full set of rapidities. Okay? Okay, and then I of course will define my group velocity as I did before. So just velocity n lambda is just T n lambda state d Pn state. But this function here will depend in the thermodynamic limit on the root densities. I mean, it depends on the configuration of rapidities, so in the thermodynamic limit it will depend on the root densities. Okay? So let me try to write down the equation for that, if I find where I wrote it. That's it. All right. So I'm writing it here, I think. So if you carry on, now let me write it on another blackboard here. It's clearer. Okay. So by the way, the full calculation, all the details are reported in the notes. There is everything. Like now I will write down this formula for the velocity, but there is a full derivation on the notes. It's a bit technical, but if you, there is also a brief explanation of Bethe ansatz. So you can try to follow it. And then if you want to ask me any question about that, I'm very happy to discuss. Okay? So now I'm just writing the result. So I'm trying to give you the idea why this thing should depend on the distribution of rapidities. And the idea is just that the theory is interacting. Okay? So let me try to write the result. And please ask if you don't understand anything I'm writing. Some function. Also, okay, I will tell you later. Okay. So you see that the velocity fulfills some self-consistent equation. Let's see if we which we combine with this equation here. Write it like this. Okay, good. Let's try to explain briefly what I wrote. Okay, so these two functions here are known. They depend on the model. So, for example, for x, z, I can write down what these functions are. So these are known functions. Okay? This function here is also known, and it is also fixed by the model. And let's first analyze this one. So this one is basically telling you what is the density of the vacancies in the state. Okay? This is a row total I was writing before. Okay? And you see that if this function t is 0, then row total is just fixed. It's some function we know. Okay? If instead this t here is non-zero, row total will depend on row.
So t depends on interactions then.
That was where I tried to go. So t is basically encoding the interactions of your theory. Okay, it's basically the derivative of the logarithm of the scattering matrix. It's like the phase of the phase shift, the derivative of the phase shift. Okay, and so you see, this is telling you something about the density of your slots, and this one is telling you something about your the velocity of excitations. And if you solve these two equations together, you find the velocity. I give you rho, you plug rho in here, you find this, then you plug this in this equation and you find the velocity just by solving. Okay. But then that's it. So if we have Yes. So, sure, but because this is not determining my root density. This is, I give you a state with some root density, and this fixes the velocity and the row total. Okay? But sure, the root density is not fixed. It's something I can give you. Yeah, it's for a thermal state, you have that, but I can give you one, and this is defining as some state. Good, but now we have everything we need to repeat the procedure of before. Yes? Of the energy difference when you make an excitation with respect to the momentum difference when you make the excitation. Yes? Yes. So you're saying I can define it from this here, or as I did now, and you're asking whether it's clear if it's going to be the same or not. That's the question. And the answer is no, it's absolutely not clear. So that's what I was trying to explain before. So this here, this expression, where V is given as I just said, is an ansatz, if you want. It's an assumption. So it's proved, it is proved in some cases, for example, integrable quantum field theories with diagonal scattering that are relativistic invariant. In that case, you can prove this formula and you show that this velocity is actually what I'm telling you. In spin chains, you have some checks and they are satisfied for this formula, but I mean, for now, I hope we will prove at some point, but for now it's not proven, okay? But it works. I mean, it has been tested many times, and all the times is always working. And this interpretation is quite simple, and it's like basically an analogy you have with a free case, and it seems to carry on. It seems to, to work. Yeah. Sorry? No, this is a very interesting question. No, it depends on the model. Like in some cases, it has been proven that is complete. In some other cases, it's just an assumption. It depends on the specific integrable model you want to consider. There are proofs of completeness of. I mean, it's a common assumption, but to have the mathematical proof of it is hard and has been done only in specific cases. To get the distribution, I mean, it's what you mean. Yeah. Yeah. It is absolutely not easy in general, and we will try to understand something better now. So, but let me first conclude the argument. So, we are all clear about that now. Since now we have an expression for the expectation values of charges and currents, we can do exactly the same as we did before. All right? What we did in the free case can be repeated straightforwardly. The only assumption we need to make is that this set of functions for different n will be complete as we did before. So basically now you can write again the continuity equation, the equation we were considering before. Okay, so we write again this equation, and now we express these expectation values using this formula. Is this clear? We want to express these expectation values in terms of the root densities specifying the stationary state using this formula. All right? So we just do it, and we get right? I just replaced these by the first, these by the second, and I rewrote the equation. Okay? Now okay, so first question. This velocity I put here, can I bring this velocity out of the derivative now? Why? That's a good point. So I can't. Let me write this explicitly. Okay? So the velocity now can't be brought out. Okay? But so if we assume that these things here are again a complete set, I can again write my equation just considering the integrand. Okay, let me just do this. Okay, so we found basically the same equation as before. Of course, also in this case, I will have the same boundary conditions I had before. So also in this case, if I take rho m of infinity, this will be given by the root densities describing the thermal state on the right. Okay? And these root densities can be computed just by using standard thermal TBA formalism. I will have a set of coupled integral equations to solve, but I will find some root densities. Let me just... And these here are determined by a set of integral equations. I mean, okay, let me not write them down. It's just, can be determined. Yes? Yeah. This is a good point. Again, it depends on the specific model. For example, for the XXZ chain has been proven. You can prove it. But this is basically related to the question of the complete GGE they addressed in the case of homogeneous quenches. Whether you can find a complete set of charges that to specify a stationary state. This is the question. So it's an assumption of the same level. So you assume that you can find a complete set of charges. And if this set of charges is complete, then that step can be performed. Show that explicitly for a specific model is hard, normally, and has been done only in some cases. But this is what is expected. I mean, this is the general idea people have, that you can fix a state using a set of local charges. All right. So, okay. So let's have a look at this equation. This equation is basically, is of course the main equation of the course. Like it's what I mean. It's the main result we are going to see in this course. And first of all, what's the physical interpretation of it? Can I still interpret it as basically a kinetic theory of free classical particles or not? In your opinion?
Yes, but weighted by some interactions renormalized or modified.
So there are two different ways to picture this equation in terms of classical particles. At least that's my view. So you can view this equation as again describing some free, non-interacting classical particles that are moving in some inhomogeneous background. So with some inhomogeneous velocity that is basically, you are given with this law that gives you the velocity in terms of the momentum distribution, and then these are just moving as free particles. But another way of interpreting the same equation is by viewing it as an equation describing interacting particles, where the velocity gets renormalized by the interactions. So they start with some bare velocity, but since they scatter against one another, they modify slightly their trajectory, and this is taken into account by the velocity depending on the state. Okay? All right. Okay, first, let me say a few words on how to solve this, and then we will try to see how it generalizes to more generic cases. So basically now we found this equation, we found our boundary conditions, So in principle, we specified our problem fully. But how to solve it is quite hard now, right? Because now, as we noted, you can't anymore take this v out of the derivative. So, well, it's a priori a very difficult equation to solve. So, there is a simple trick you can make to simplify a little bit the solution of this equation. And this trick is to introduce another function. So, if instead of rho, you introduce a function that we call normally theta, that is the ratio of rho and this vacancy density, defined here in terms of rho, okay? So you define this function called the filling, normally filling function. You find in a very simple step that is one of the exercises, if you want, that the filling function satisfies the simple equation. We had in the free case. So basically, it satisfies something like this equation where we can bring V out. This seems like magic, but I mean, it's true. But, so of course, now I can write the solution, at least formally. I'm trying now. I'm sorry. There will be some problem in the notation that we will try to sort out. Okay. So unfortunately, I'm using theta for two different things. Like. So you can formally solve this equation as we did before. The solution, formal solution to this equation is again a step function. So it's like this, okay? So it's some filling function on the left time this, I'm trying to write it in a different way. This is a step function, okay? So it's still theta, but it's uppercase theta. I'm not sure, you can distinguish it, I hope so. Okay, so the formal solution is this. But question, is this a solution? So am I done? Can I go home? Probably yes. Exactly. So this is not a real solution. This is just okay. So but this is still helping. This is still helping because if I number things 1, 2, okay, what I do is the following. I take some guess, I guess initially some velocity. So step A. Okay. B, I plug it in 1. And find theta. C, I plug theta in 2. and find the new v. And then I start again. With point B. Okay? Guess V, find theta, plug theta in here, and find, sorry, here, of course, I can write this in terms of theta just by writing rho total here. This is theta, this is rho total, and this is, and I put theta, okay? Right? So I find theta, I plug theta in here, I find the new V, okay? And I go on. So, goes to point B, yeah, goes to point B. And this iterative procedure, I mean, it works quite well. It converges quite fast. And you can try to you construct your solution in an easy way. So let me make a few remarks before moving to the last point. So what we did here is we basically constructed this stationary state in the case of the bipartite quench consisting in the sudden junction of two thermal states. But the same procedure here, what I did, doesn't really depend on the fact that I put two thermal states on the two sides. I could have put anything. Yeah? You mean this procedure? Well, when you reach convergence, when you basically produce a velocity profile that doesn't change anymore. I mean, no, it's a numerical procedure. So you just, I mean, you take a finite number of steps chosen in such a way that the velocity profile looks the same. I mean, yeah, there's no, I mean, it's iteration. So I was saying, okay, so at the end of the day, this thing can be done all the times. I can determine my boundary conditions, okay? So, of course, TBA offers me a very simple way to determine the boundary conditions in the case of the sudden junction of two, or the junction of two thermal states. But I can also consider cases where I join two non-stationary states, so that far away from the junction, the problem looks like a homogeneous quantum quench. And in many cases, like there are, let's say, examples where after a homogeneous quantum quench, you can determine this feeding function theta. And so that will also allow us to apply this formalism and find our ray-dependent distribution. Okay? Okay. Sorry? Yeah. So, what's the, I mean, of course, I see, yes, yeah. So basically, I mean, everything we did was we assumed that in the scaling limit we considered, everything becomes like all the expectation values of local observables can be expressed as expectation values on a stationary state. This is the assumption behind what we did. So, of course, one might ask, can we prove that in the generic case? So in the free case, that's the meaning of our painful calculation of last time. So we proved that. In the interacting case instead, that's much harder. But this is the same problem you have again for homogeneous quantum quenches. For homogeneous quantum quenches in the interacting case, you are not proving that you relax to a stationary state. You are assuming that and determining it. Why? Yes. Well, but everything comes down to the ray. It's just my limit. I'm taking a scaling limit. So I'm sending position and time to infinity, fixing the ray. So everything, I mean, there is the only additional dependence can only be on the ray. But I agree with you. I mean, this is it's not a priori clear that everything will be written as a stationary state. Of course, this is a yeah. It's the same assumption you make in the homogeneous case. But this is an assumption. Yeah, in the interacting case, this is an assumption. And basically, the only way to test this assumption is to compare with some numerical result. There is no other way. But, okay, so let's now try to consider something, some outlook for this. So, what are the things that outlook open problems? Okay, so some we already mentioned. So first, prove that that's exactly what Yuri was talking about. This is an open problem. For all this is our ray assumption, and again, this is something in principle somebody could prove, even if it's quite hard, I think. Another thing that is open is to prove the formula for currents in general. Okay. So these are on the technical side, but there is much more interesting stuff, which is the following. So here we studied a very specific scaling limit, where everything, I mean, making these assumptions, apart from this assumption, everything becomes exact. Okay? So like what I'm telling you is believed to be exact. But you can apply this formalism in much more generic situations. Okay? So you can apply this formula when your initial state is inhomogeneous of some form. And in that case, what you do is the following. You say that the trace, that the expectation value of your operator what you assume is that the expectation values of your local operators, when you take the position and time large, are described by a stationary state, at least approximately. Okay? And this stationary state, it depends slowly on time and position. Okay? Note that this is different from what we did, because here we are really putting the equal sign. Here we are really saying we take this limit, and in this limit we claim that this is exact. This won't be exact. This is an approximation. And this is the, let's say, basis of the thermodynamic, of the hydrodynamic description that Jerome was talking about in his lectures. Okay? You can make an assumption of this form. And if you do that, you find that our equation, which I erased, I think, can be written instead of as a function of the ray, as a function separately of time and position. So I'm just going to rewrite the same equation, but now I'm not using the ray, I'm using t and x separately. And you find an equation of this form. To determine this state, okay? Now this root density will depend on position and time, separately, not on the ray, okay? But in this case here, of course, I will have some corrections. There will be something of the order 1 over t to some power, and 1 over j, x to some power. Okay? There will be some subleading corrections here. Because here I took really the infinite j and t limit in order really to kill this thing. So I really took it's like, you can think about this as a homogeneous quench problem again. So if you take exactly the t to infinity limit, then you go to the stationary state. But if you don't take it, you take t to be very large, then your state is approximately described by the stationary state, but you still have some time dependence, right? That's the same idea. So you take t large, j large, but not to infinity, because to infinity in general, if you just take the exact limit, your problem becomes trivial. For example, you can think of releasing a gas from a trap. So if you want to describe the situation where you have some gas of particles, so you have some gas of particles initially contained in some potential, and then you switch this potential to 0. Okay, so you will have some bunch of particles here expanding. Okay. Of course, if I take the limit t and position to infinity, this problem becomes trivial. I see nothing, just a 0 density. Yeah, but of course. But I'm just saying that in many interesting cases, you can't take the infinite j and t limit. You need to work at some finite t and position. Otherwise, you just describe nothing. Okay? But in that case, of course, you will have some corrections to this equation. And the interesting question at the moment is to try... Oh, sorry, yeah, please. No, it's not. I mean, it's a reasonable assumption, but it's not obvious. This is based on, for example, what happens in free systems, like the KF power law. In free systems, you can determine them, of course, and yeah. But this is just. But so I was saying, you will have some corrections. So that's basically in another language, I think, what also Jerome was talking about. So this will give you the Euler scale in Jerome language dynamics, but then you will have all the dynamics at shorter scales that can kick in. In particular, there are some like very interesting results recently that managed to find one of those corrections, where you add basically a Navier-Stokes term to this equation, a diffusive part. Okay, so something depending on the second derivative of x. you understand immediately that if you have a second derivative here, this scales differently than from that. So in the large x and t limit, the second derivative doesn't matter. But if I take x and t finite, even if large, this can be important. Okay? Of course, then a very exciting problem at the moment is actually determining this correction here exactly. So there is this very interesting result by Jacopo De Nardis, Benjamin Doyon, and Denis Bernard from this year. Oh, sorry, from last year. Now it's 2019. Where they determined some diffusive correction to this equation. Sorry? I mean, they did the calculation for Liebling, but they claim they wrote this correction in terms of rows. So they say, okay, this is a general TBA correction. Okay? And question? Yeah.
Could we expect that so the scaling limit which shows that if j of t fixed with just rays, like it somehow assumes that you have this quasi-particle picture and then you have
Yeah. Yeah.
So if I'm interested in diffusion, I would expect that I take the diffusive scaling as people.
Mm-hmm. Yes, it makes sense. No, it makes sense that you can define, for example, for this bipartitioning protocol I was discussing in the course, you can try to study, instead of the limit I was talking about, the limit where instead you scale position at the square root of time. So in order to see the diffusion. Well, I mean, if I take the correction found in this paper here, I can in principle describe that. I have an equation to describe that. No, I mean in general I have the ballistic term and this diffusive term, and the diffusive term will be basically like invisible if you have the ballistic, But in some cases, the diffusive term becomes trivial, so it's just, the ballistic term becomes trivial, and you see only the diffusion, and in that case, you can actually, yeah. For example, if you study spin transport in XXT, in some cases, it's actually diffusive, so basically at the ballistic scale, you see nothing, you see just a step when you do this bipartitioning protocol, and you should go at this different scale you were mentioning to see some smooth function. Okay, so, and good, but like to conclude, actually you can use this equation to describe actual experiments. And that's what Jérôme did. So what Jérôme did was, probably, I'm not sure I have time to show you the picture, but I'm sure he will do. But he applied this equation here to describe an experimental setting. So they did many things, and I will let him describe his work, but basically they did something similar to what I was trying to picture here. They consider a gas of rubidium atoms in a trap. They release the trap, and they study the expansion using this equation. And they showed that basically this equation gives you a much more accurate description than the one of standard hydrodynamics. Okay, so this equation actually is not only, let's say, an interesting theoretical result, but is helping us to describe actual experiments. And this is, well, interesting. So, well, I think I can conclude here. Yeah, okay, thank you. No question. One question.
Where would be the next challenges? Where would you envision the field going in terms of probably like determining more of the diffusive limit, or like in a sense, what excites you personally, and like where did you, in a sense, find your own vision in quantum dynamics?
Yeah, I think that at the moment, so this is exactly what I was trying to describe in the last part of this lecture. So I think that at the moment, a very interesting question is to understand whether you can apply this approach in a rigorous way, also out of the protocol I was trying to describe during this lecture. So you need to find these corrections, and but this is, if you think about it, quite interesting, because so basically what we showed is that at this Euler scale we studied, there is no big difference between quantum and classical physics. At the end, the only information about the quantumness of our model is contained in this velocity. But of course, you can, which I mean obeys complicated integral equations. But you can find very easily, and actually has been done, a classical model that fulfills exactly, that gives you a rest velocity fulfilling exactly the same equations. And so, I mean, you can basically say that at this level, you really don't see any quantum correction, any different. And it would be interesting to see whether, I mean, these things, this property is just continuing to hold at all orders, or at some point, I don't know, quantum corrections will kick in and will be important for something. And
Quantum corrections will always be some small correction of the mean field, or like to the, in a sense, yeah, to a thermodynamic, well-defined thermodynamic limit, right? I mean, could you see this being subverted?
so you mean,
So where, like, yeah, quantum correlations or corrections in a sense would alter macroscopically sort of what is asked of.
well, it doesn't, I mean, it doesn't seem, I mean, whenever you can apply an hydrodynamic description, basically you are saying that this is not true. And in this case, what this equation shows is that you can apply an hydrodynamic description. So no, you don't expect these quantum corrections to overwhelm. And I mean, but I don't. Yes. Of course, I mean that's a good question. So this thing here doesn't need, as I try to stress many times, like this when I say more general setting, okay, the meaning of this more general setting is a more general initial state. Okay, so for example, this state here doesn't look like a bipartition. You start with a bunch of particles at some point and you let them expand. Okay, but then you can ask, and it's a very reasonable question, this. There will be some condition on the form of the initial state. I will not be able to apply this equation to all possible initial states, right? You can ask that. And this is a very good point. Indeed, there must be a scale of variation, let's say a scale, like a measure of the homogeneity of this initial state. So for a state that is too much inhomogeneous, this treatment here will not be very sensible, because it depends on a higher derivative with respect to the position. So if it's really like varying on a very short scale, I expect this equation to be extremely inaccurate. Sorry? No, no, but wait a second, let me finish. So the point is that time will cure this. Time will cure this. So if I wait long enough, I expect my state to smoothen out. And then I expect to be able to apply this. And that's exactly what happens in the bipartition protocol. So at the bipartition protocol, I have a sudden jump. So if I try at the beginning to apply my equation, I get garbage. But if I wait long enough, and this long enough is not really long, I can apply my equation. So I expect something similar. But that's the point. I mean, maybe your state is so inhomogeneous and complicated that you need to wait very long times after like you can apply the equation, and then the situation becomes trivial, or like corrections you find. Yes, sorry.
Yes, so usual hydrodynamics also shows that what does local observables is that correlation function even into a global trend. So would you expect something similar here?
We need to first of all, we need to specify what we mean by correlation function. So you mean initial protocol, I can study correlation functions if the two, let's say, observables live on the same ray. So if the position of the two observables go to infinity at infinite times, like the relative distance, the distance between the two doesn't grow with t. This I can still study because it becomes a local observable for me. Then you can ask another question, which is also interesting, is what about instead correlations among different rays? It is encoded. Okay, so if you are asking about the correlations on different rays at the same time, no, it's not encoded. It's some subleading correction, and it's going to zero as some power of some like power law in time. So I don't see it in this approach. But if you instead look at dynamical correlation functions, then yes, there are also some works describing them using hydrodynamics. There is some like there is a work of 2017 by Benjamin Doyon, I think alone, and you can have a look. It's a discussion of these kind of things. Okay.